We now move on to the volume of a cuboid and a cube. So we are done with the surface area, and I hope you are able to do the sums that you are getting from the reference books or from any other sources. So volume of a cuboid, the basic definition is the space that a cuboid occupies. So if you're talking about any solid for that matter, volume basically refers to the space that the solid occupies or the capacity of the given solid. Suppose the solid is a hollow solid and we need to fill it with water and they are asking you the volume. In that case, it means the capacity or the amount that a solid can hold, whether it be liquid or solid, whatever it is. So basically, volume refers to the space that a solid can occupy or to the capacity of a solid. Okay. Now, let us move on to the volume of a cuboid. Now, this is our cuboid. The volume of any solid is given by the base area into the height of the solid. Now, the base area of the cuboid is L into B into the height of the cuboid. That is a space that it occupies. Now, it does not matter how you keep the cuboid. Suppose you are keeping this as the base of the cuboid, then also you will get base into height, then the length becomes the height into L. So, the final formula will inevitably remain the same. It is length into breadth into height. So, for our mental ease, we always take L into B as the base into the height. That gives the volume of a cuboid. In the case of a cube, since L, B and H all are equal to each other, my volume of a cube becomes L cube. Okay. Now, one important point that you need to keep in mind is that whenever you are converting a solid from one shape to another, suppose you are converting a metal cuboid from the cuboid shape to a cylindrical shape. Okay. You need to keep in mind that the volume of the cuboid will never change even though it will change the shape. Fine. If you have the volume of a, suppose you are converting this cuboid into a cylinder. Okay. The volume of the metal in the cuboid when it is converted into the shape of a cylinder will not change. The area will change, but the volume will not change unless specifically they mention in the question that this much of volume is lost. Okay, so this is one point that you need to keep in mind whenever you are getting a question in which one shape is converted into another shape. Now let us do a few basic sums and then a few more complicated sums on the volume of a cube and a cuboid. The capacity of a cuboidal tank is 50,000 liters. Length and depth is given to you. You have to find the breadth. Now, as in any sum we are doing with respect to surface area and volume, I always told you please check the units. So in this case, the capacity is given in liters, but the length and the depth are given in meters. So we need to convert the capacity into centimeter or meter cube. So for that particular conversion, we need to use this. 1 meter cube is 1000 liters. So that is a conversion that you need to study, and same in the case of surface area, we need to study how to convert a centimeter into meter or a decimeter into meter, etc., depending upon the unit that you are comfortable using. Fine. So the capacity of a cuboidal tank is 50,000 liters. So I need to convert it into meter cube. I know that 1000 liters is 1 meter cube. Okay. Or I can say that 1 liter is 1 by 1000 meter cube. Fine. So here I have got how many liters? 50,000 liters. That is 50,000 by 1000 meter cube, which is 50 meter cube. So the capacity or the volume of the cuboidal tank is given to be 50 meter cube. Sorry, L into B into H is 50. Or I can say that 2.5 into B into 10 is 50, or B is equal to 50 by 25, which is 2 meter. So in this particular sum, the main concern would be to convert liters into meter cube, after which it is a very straightforward sum, basic multiplication and division, right? How many 3 meter cubes can be cut from a cuboid measuring 18 into 12 into 9? So we are given the dimensions of the cuboid. We know that the cuboid, when it is converted from one shape to another, I told you that the volume will not change at all. So what is the volume of the cuboid? Volume of the cuboid is equal to volume of the cubes. Okay, we don't know how many cubes are there. Let there be n cubes into, right? So what is the volume of a cuboid? It is 18 into 12 into 9. And what is the volume of a 3 meter cube equal to? It is n into 3 cube, which is 3 into 3 into 3. Okay, so I get the value of n as 18 into 12 into 9 divided by 3 into 3 into 3. So what do I get? I get 72. So I will get 72 cubes from this particular cuboid. Now I will be discussing the basic concept of a cuboid or any solid for that matter filled with liquid. In this case, we are, most of the cases, unless very specifically mentioned, we always assume or take it that water is a liquid that is filled in the solid. Now the question comes when they mention that there is a solid which is immersed in water contained in another solid. So let us go through the concept and what formula we need to use when we are getting any sum like this. When you have a cuboid, you know that the cuboid has a volume which is given by L into B into H. Okay. I told you that the volume basically means the capacity of the cuboid. So when you have water inside the cuboid filled to the brim level, filled in completely. So what is the quantity of water which is contained in the cuboid? It is L into B into H. Okay. Suppose the water is not filled to the maximum level. Water is filled only to a height of H by 2. What is the volume of water? So it will be L into B into H by 2. What is the volume of the cuboid? It is L into B into H. Because water was only till half of the height, the volume of the water is L into B into H by 2. But the volume of the cuboid is L into B into H. So which means that I can pour in more water to the cuboid. Okay, that part is clear. Now, you know that if you take a bucket of water and you put a big stone in it, what will happen? The water will rise. There is a case with the water contained in any solid. If you are dropping another solid into it, the water will automatically rise. What is the amount of water that will rise is dependent upon the volume of the cuboid or volume of the solid that we are putting into the water. Fine. Suppose we have a cuboid filled with water. So we don't know what is the height of the water. We have a cuboid and there is some water in it. Let us say up to a height of H1. So what is the level of water? What's the volume of the water? It is L into B into H1 because only the height will change. Nothing else will change. What's the volume of the cuboid? It is L into B into H. I told you already. Suppose you are dropping a stone of volume V into this water. What will happen to the water? It will automatically rise. Okay. How much water will rise? The rise of water will be equal to the volume of the stone or will be corresponding to the volume of the stone that you are dropping inside the liquid. Okay. So, volume of the stone is equal to volume of the water that rose. Correct. Now, this water was inside which solid? It was inside a cuboid. So, this will be corresponding to the formula L into B into the height of water rise. Okay. So, whenever you have a vessel which has got water, they will be giving you the shape of the vessel. It could be a cylinder, it could be a cuboid. You need to understand that water has got a volume. When you are dropping a solid into it, the solid has got a volume. So, our basic idea is volume of the dropped solid is equal to volume of the water that has risen up in the solid vessel, so that you differentiate between this solid and this solid. Okay. Now let us do a sum so that you get the idea clear. I am not very sure whether you have gotten this concept clear. So let us anyway do a few sums. Let's start from the basic. A cuboid vessel has dimensions 12 meter into 10 meter into 5 meter. Water is filled up to a height of 3 meters. Find the remaining volume. Okay, from the basic I am starting. So you know that the cuboid vessel has got a volume. Sorry. So volume of the cuboid is 12 into 10 into 5. So I will get 120 into 5, 600 meters square. This is the volume of the cuboid. What is the volume of the water in the cuboid? It is 12 into 10 into 3, which is 360 meters square. So what is the remaining volume? 600 minus 360. Okay, so you are very clear with the volume of the cuboid and the volume of the water in the cuboid. Both are two separate entities. Okay, now let us move on to the next sum. It's the same sum, but I have added a stone to it. Cuboid vessel has a dimension, so water is filled up to a height of 3 meters. A stone of volume 100 meter cube is dropped into the water. Find the volume of the empty space in the vessel. Okay, so what is the volume of the cuboid? We already found it out, which is 600. I'm sorry, meter cube. Okay, water is filled up to a height of 3 meters. Volume of water 12 into 10 into 3, which is 360 meter cube. Now we have empty space. Definitely yes. Stone of volume 100 meter cube is dropped into the water. What will happen to the water then? It will rise by 100 meter cube. The reason being 100 meter cube volume is added to the already existing quantity of water. So volume of water rise is equal to volume of dropped stone, which is 100. Now final volume of water is what? It is 360 plus 100, which is 460 meter cube. Now what is the remaining volume? Now the remaining volume is 600 minus 460, whatever we are getting. So are you clear? So whenever we are dropping the stone into the water, that water which is displaced, that volume will be equal to the volume of the stone. Okay, now let us give another twist to the sum and see how to do it. Now I have changed the question slightly. So a stone of volume 100 meter cube is dropped into the water. Find the rise in the water level. So you know that obviously the water level has risen. So the volume of the water rise is equal to volume of the stone dropped, that is 100 meter cube. Now the water is contained in the cuboid. So suppose this is a cuboid and this was the original level of water. After the stone was dropped, this is the height through which water level rose after dropping the stone over here. Okay, now this water has a volume. That volume will be in the shape of the cuboid, which is L into B into H again. Okay, so volume of the water rise is volume of the dropped stone. So 100 is equal to volume of water rise in the cuboid, that is L into B into H. Right? So I know the value of L, I know the value of B, I need to find H. So what will I get? H is equal to 100 by 120. So what am I getting? I am getting around 5 by 6 meters. So converted into decimal. So I hope you have understood the basic concept of doing this kind of sums. So let us move on to a sum with proper values so that you get a proper answer for the height. Okay. A cuboid vessel with water has length and breadth as 15 meters and 12 meters. A cube of 3 meter edge is dropped into the water. Find the rise in water level. So here they have not even given the height of the cuboid vessel. The reason being we don't need to find the volume of the cuboid or the volume of the water existing inside the cuboid. We only need to find by how much height the water has risen. Okay. So the basic concept is volume of the dropped cube is equal to the volume of the water that has risen in the cuboid. What's the volume of the cube? It is A cube or L cube, which is 9 into 9 into 9. Volume of the water that has risen in the cuboid is L into B into H. H is the height by which water has risen. So I get 15 into 12 into H, or my H is equal to, okay, so you will get 81 by 20. It is not going to be a proper value. You are going to get it in decimal. Let us see what we are getting. Okay, so now you are clear with this kind of sums wherein, the water rise is given to you. You also need to remember that when you take out the solid which is already inside the water level will go down. The same concept has to be used over here. The volume of the solid is equal to the volume of the water loss. Okay, and then we have to equate them and find the required drop in water height. It is the same logic. In this case, we have talked about the rise in water level. But when the solid is taken out of the water, we need to understand that it is a drop in the level of water. Okay. Now we are going to talk about the sums wherein water is flowing in a canal or inside a pipe into a rectangular plot or into a reservoir. Water from a reservoir is moving into a pipe, etc., etc. So in this type of sums, our basic idea is this. In this kind of sums, as I told you, there will be a canal or there will be a reservoir. Now we need to understand what is the shape that we should take for the canal or the reservoir. We always take the canal to be a cuboid. Now the reason is, what is a canal, right? It is a path for free water flow. In irrigation fields, if any of you have any time gone to an irrigation field and you have seen a canal, you know what I mean. There is a, it is at a depth and there is free flow of water so that the entire region is irrigated. So this is basically the shape. You know that there is a mouth of the canal, or you can say there is a width of the canal. We are assuming that the width of the canal will remain the same everywhere. Okay. Now this is the length of the canal. Now when I say the length of the canal, you need to understand that by the length of the canal we basically mean the distance covered by water. So because the water is not stationary and it is flowing, in this case, the length of the canal is basically the distance covered by the water. This is the main point in this kind of particular sum that you need to remember. The length of the canal, if by the length of the canal, we need to find the distance that is covered by water. Okay. Now, you know that when there is a canal, there is a depth. The depth, see, if you have been to, as I told, if you have been to an irrigation field, you have seen your parents or the elders in your family saying, do not venture into the canal because it is deep. It is like a river. Do not get into the river because it is deep. So there is a depth. So you have three measurements: length, breadth, and height. Height means the depth. Okay. So I can safely say that my canal is in the shape of a cuboid. Now a cuboid has a volume. So if I am asking you what is the volume of the canal, it is length into breadth into height. Okay. So I hope you are clear with why we take the canal as a cuboid and how to find the volume of water inside a canal. Okay. Now that I spoke about the canal, you also need to understand that this is the same case with water flowing in a pipe. So canal or a pipe, wherever there is flowing water, we need to take the length according to this. Okay. If you are given a reservoir or a water tank where the water is stationary, they will directly give you length, breadth, and the height. Okay. So you know how to differentiate between these two. Now, normally when they say a canal, it is for irrigating a field. So what they say is that water flowing in a canal is flowing into a field. Now, you know that field is in the shape of a rectangle. Unless I specifically mention it is a triangle shaped field or something like that, it is a rectangle. Now, a rectangle got a length and a breadth. Okay. Now, you know that we are dealing with three-dimensional figures, right? So, where does the height come from? So, what they usually say is that the water flowing in the canal or the pipe or the water from the reservoir moves into a rectangular field, moves into the irrigation field where a particular height of water should be maintained. So which basically means they expect us to fill this region with a particular height of water. So if there's a 10 centimeters of water or 2 centimeters of water, you need to know that H value will be that particular one. Again, that is a cuboid. Okay, I hope you have got the basic concept clear. Now let us do a couple of sums so that you know how to apply the concept. Water in a canal 30 decimeter wide, 12 meter deep, flows with a speed of 10 kilometer per hour. 20 kilometer per hour. Sorry. How much area will it irrigate in 30 minutes if 10 centimeters of standing water is required? Okay, so 30 decimeter wide. So B is given to you. Okay. 12 meter deep. So you know the depth or the height is equal to 12 meter. Okay. Now, in order to find the volume of this particular canal, which is in the shape of a cuboid, I need to find the length. As I told you, when it is flowing water, length is equal to the distance covered by water. Right? So, you know velocity is distance by time. So, distance is equal to velocity into time, or speed is equal to distance by time. Distance is speed into time. So, now what is the speed? The speed of water is given to be 20 kilometer per hour. And the time is given to be 30 minutes. Okay. Now, this is the length of water in the canal. Now, you can see that breadth is given in decimeter, height or the depth is given in meters, and this is given in kilometer per hour, and the time is given in minutes. Now, our first task is to convert all of them into a proper unit which we can apply across the sum. So, guys, I have converted B into 30 decimeter into meters. You know 1 decimeter is 1 by 10th of the meter. So 30 decimeter is 30 by 10, which is 3 meters. My height or the depth, I don't have to convert because it is already in meters, 12. Now I have a problem with the length because length is given by speed into time. My speed is in kilometer per hour. How do you convert kilometer per hour into meter per second? I will have to multiply it by 5 by 18. So 1 kilometer per hour, you need to multiply it by 5 by 18 in order to convert it into meter per second. So 20 kilometer per hour, I multiply by 5 by 18 in order to get 50 by 9. I am retaining the fraction as such because I am not going to get a proper number for this, right? So 50 by 9 meter per second is my speed. Now 30 minutes, because it is in meter per second, I need to convert the minutes also into seconds. I multiply by 60. So this is the length. Now I am going to find the volume. So my length is this, 50 by 9 into 30 into 60, 10,000 meters is what I am getting. Right? Now, what is the volume of the canal? It is L into B into H. So I am getting 36 into 10 raised to 4 meter cube as a volume of my canal, which is in the shape of a cuboid. Now what is the question? How much area will it irrigate in 30 minutes if 10 centimeters of standing water is required? So this water from the canal, which was flowing for 30 minutes, is going into a rectangular field. As I told you, it is the shape, it has a length as well as a breadth. Now, if 10 centimeters of standing water is required, so we need to find the area of the rectangular field, which is given by L into B. Okay, that is what we need to find. So, what is the volume of the rectangular field? Volume of the rectangular field is L into B into the height of the standing water. Now, the height of the standing water is given as 10 centimeters. So, volume of the rectangular field is equal to L into B into 10. Okay, now this 10 is given in centimeters. We need to convert it into meter, divide by 100. So here you can see that I have equated both the volumes, 36 into 10 raised to 4 into the area of the irrigation field into the height of the standing water. So when we solve this, we will get the area to be 36 into 10 raised to 5 meter square. Okay, so this is one sum. So I hope you have understood how to apply the concept of flowing water and the flowing water flowing into an irrigation field which is in the shape of a rectangle. Now let us try out a couple of more sums so that you don't have to worry about how to apply this particular concept to this kind of sums. Rectangular water reservoir is 10.8 meters by 3.75 meters at the base. Water flows into it at the rate of 80 meters per second through a pipe having a cross section of so and so. Find the height to which water will rise in the reservoir. Okay. So water is basically flowing into the reservoir. So I have a reservoir, whatever the shape is. Now there is a pipe. Now this is still water. So I can safely use the formula L into B into H. Pipe, you have a flowing water. So I need to use the concept of speed into time. Okay. As soon as you get the sum, get these two things clear inside your head. Okay. Now let us deal with the reservoir first. But before that, the units: meters, meter per second, okay, centimeters and centimeters. Now we are having a problem with the unit over here. So since three of them are in meters, you need to convert this also into meter. It is an irritating thing because it's already in decimals, but then we will just write it as 7.5 by 100 and 4.5 by 100. Okay. I will maintain it as fraction itself, but when you are writing for the exam, please write the cross section as 0.075 meters and 0.045 meters. But while doing the calculation, if you find it easy, convert it back like this and do the calculation. But for your teacher, for presenting the sum, please write it like this. Okay. Now let us get on to the sum. Still water, L into B into H. So the reservoir, rectangular water reservoir, has a base of 10.8 into 3.75. So 10.8 into 3.75, and we need to find the height to which water will rise in the reservoir. So into H, because H is what we need to find. So keep it there. Now we have the volume of the pipe over here. Now you have flowing water. The length of the pipe is given by the distance covered by the water, which is speed into time. So what is the speed of water? Water flows into it at a speed of 80 meters per second into time. Now, for how long is the water flowing? Forgot to write the time, which is 30 minutes. So I will get 18 into 30 minutes. I am retaining the time as minutes itself. Oh yeah, here I have got a second over here. So I have to convert it into seconds, into 60. So I will get 18 into 1800, which is 32400, so much of meters. Okay, so that is the length of the pipe. So now after getting the length of the pipe, 32400 meters. Now I have got the breadth. I have got the breadth and I have got the height. Equate the volume of the pipe to the volume of the reservoir and find the value of H. So I will be doing the calculation, and meanwhile please do the calculation and try to do the sum on your own. I have equated the volume of the water in the pipe to the volume of the reservoir. I need to find out the value of H. So what I have done over here is that I have cancelled off the 100 over here itself, the two zeros over here. So the remaining 324 into 7.5 into 4.5 divided by this will give me H. Okay, now for this one particular sum, I will just show you how I move on with my calculations. If that is of any help to you, you can please follow that method. If not, you totally follow your method, whichever is convenient to you. Okay, so what I do is that I first of all convert all the decimals into proper numbers, because I really cannot work with the decimals. I have told you, I try to avoid decimals whenever possible. So what I do is that I multiply the numerator and the denominator by 100. Here also I multiply. I don't have to multiply with 100 because I have already 100 over here. But still I have, because I have multiplied the numerator with 100, I have to multiply the denominator also with 100. So I get 108 into 37.5 into 100. Okay. Now I have got one more decimal over here. In order to avoid that, I will do 324 into 75 into 45 by 108 into 375 into 10. Okay, this is how I have broken it down by the way. So You know that 108 into 3 is 324. If you are not able to figure that out immediately, you know that 18 into 18 is 324 and 18 into 6 is 108. So that way also you can do. So by cancelling out the common factors, but since I already know 108 into 3 is 324, so I get a 3 over here. Okay. Now I will check whether this is divisible by 3. I can say that the sum of the digits is a 15, so it is divisible by 3. So I divide by 3, I get 3. I get a 125. Okay. Now all the terms are divisible by 5. So I will try to divide this by a 5. I will get 25. I will try to divide this by a 5. I get a 3. I will get a 9. Okay. Now 25 and 75. I know that I can cancel out the common factors. So what do I get when I am cancelling 25 and 75? I will get 3. Okay. Now it is very simple. It is 27 by 10, which is 2.7 meters. This is our answer. Now this is just the way I calculate, and some people I have seen, some of my students are very good with decimals. So when I convert the decimals into fractions, they will say that it is just not possible for them to work with fractions. They go back to operating the whatever calculation with the decimals. So depending upon how you are comfortable with that, you can find only when you do more calculations, figure out your way and then do the sum. So whether the water is flowing in the reservoir or whether depending upon whether the water is flowing from a pipe into the reservoir or from a canal into an irrigation field, whatever. So you know how to break down the concepts and then simplify it and apply it to the sum. Now I am done with this kind of sums because although I did only 2, I think it is more than clear for all of you. So you can practice more sums either from the NCERT book or from any of the reference book. And if there is any doubt regarding the concept, do get back to me. Now the next kind of sum, we will take a break from this kind of sums and we will move to a very easy kind of concept regarding the volume of cube and cuboids or any shape for that matter, is converting one shape into another shape. Now I told you that the volume will not change if you convert a cuboid or a cube into a cylinder or into a sphere or anything. The content or the amount of metal that is there in one shape will definitely will be the same in the next shape also. So the volume, the basic idea is that the volume remains the same across, though the surface area, total surface area will definitely change depending upon the shape of the solid that you are having. So let us do a couple of sums and see how we can apply it. 3 metal cubes of size 3 centimeters, 4 centimeters and 5 centimeters are melted to form a cube. Find the surface area of the cube. Now, whenever you have this word melted, remolded, converted, it means that the volume remains the same. So I can say that volume of 3 metal cubes is equal to volume of the single cube. Okay, we do not know anything about the side of the single cube. So let me take the side as a, okay, 3 metal cubes. So one metal cube of size 3 centimeters, the second one of size 4 centimeters and the third one of size 5 centimeters. Right? So what do we get? 27, sorry, 64 and 125 will give me a cube. So let us see what is the value of side that we are getting for this particular cube. You get the value of the side of the new cube as 6 centimeters. So what do we need to find? We need to find the total surface area, which is given by 6a square, which is 6 into 6 square, which is again 216 centimeters square. Okay, this is one of the very basic sums in this particular concept. So we will do a couple of sums more in order to get this idea very clear for you guys. Before I move on to this particular sum, just have a look at this. Okay. This is a cuboid. This is the length of the cuboid. This is the breadth of the cuboid. And here you can see this post-it, there is a depth. Okay. So here I have the H. Suppose I want to break this cuboid into 2 parts along the length. 2 equal cuboids along the length. What do? I make a cut exactly over here so that this becomes 2 parts. right? Now, what can you say about the length of this part? Because it is exactly half, I can say the length is L by 2. But I can see that the breadth and the height remains the same. So it's the same with both the cuboids. Okay. Now, suppose I am having a cube. It does not matter whether I am making the break along the length, breadth or the height. Since all the sides are equal, I can say that if A is the side of a cube, suppose I am making it into two cubes along the length, breadth or the height, I will get one side as A by 2 and the remaining two side as A. Okay. In the case of a cuboid, if I am making the cut along the length becomes L by 2, breadth and the height will remain the same. Suppose I need to cut the cuboid like this. So I get two cuboids like this. My length will remain the same. My depth will remain the same, but my breadth will become B by 2. Okay. So whenever you are making two cuboids out of a single cuboid, you need to know whether you are cutting it along the length, breadth or the height. But in the case of a cube, you do not have to make any such differentiation, because wherever you are making that split along the cube, the length, since all the length are the same, that specification does not matter at all. Okay. So now let us move on to the sum. A solid cube is cut into two cuboids of equal volume. Find the ratio of the TSI of the cube and one of the cuboids. So here we are making a clean cut on a cube. So a cube of side A, all the sides are A, everything is A. Okay. I am making it into two cuboids. Suppose I am cutting the cuboid along the length, the cube along the length. So my length, which was originally A, will become A by 2. What will happen to my breadth? It will remain the same. My depth also will remain the same. Suppose I am making the cut of the cube along the breadth. My breadth will become A by 2, but my length and the height will remain the same. Clear? So in this case, we got two cuboids out of a single cube. They are having equal volume. Okay. Now find the ratio of the TSI of the cube. What was the TSI of the cube? It is 6A square. Now, one of the cuboids, we need to find the TSA. So the TSA of a cuboid is given by 2 into LB plus BH plus LH. Now, my length became A by 2. Breadth remained the same. Breadth is the same. Height is the same. My length became A by 2 and height. So what do I get over here? 2 into A square by 2 plus A square plus A square by 2. So I will get 4A square. Okay. I need to find out the ratio, which is 6A square by 4A square, which is 6 by 4, which is 3 by 2. So here is our next sum. Half cubic meter of gold sheet is extended by hammering so as to cover an area of 1 hectare. Find thickness of the gold sheet. So what is given to us? The measurement that is given to us is the volume of the gold sheet. Volume of the gold sheet is given to us. We know the volume of the gold sheet is given to us by looking at the unit that is given to us, which is cubic meter or meter cubed. If it is square meter or meter square, we know the area specification is given to us. Here we know that half cubic meter of gold sheet is extended by hammering. So when we keep on hammering a sheet of metal or something, it will get extended. Okay, so here the gold sheet is also extended by hammering. So we have got half meter cube of gold sheet is extended by hammering so as to cover an area of 1 hectare. So volume of gold sheet before hammering is equal to volume of gold sheet to cover 1 hectare. Okay, I told you whichever shape the metal is in, the volume will not change. So here our main problem is changing the unit from hectare to meter cube. So meter square. Hectare is a unit of area. So what is 1 hectare equal to? 1 hectare is 10,000 meters square. And when we are covering 10,000 meters square with gold sheet, there is a thickness for the gold sheet. So this area into the thickness, or let me write it as thickness T, will give you the volume of the gold sheet used to cover 1 hectare. That is equal to half meter cube. Okay. So how do you find the thickness? Thickness is half by 10,000. So let us see what we are getting after the calculation. So I have gotten 1 by 200 centimeter as the thickness of the gold sheet, which was covering the 1 hectare of area. Okay. Our next type of sum is the sums wherein a particular amount of sand or earth basically means the mud part of it I am talking about, it is taken out from a field and deposited in another place. Okay, here also when we are taking out earth or sand from a particular place, we are taking a volume of the sand, a quantity of the sand which actually is measured in terms of volume of the sand. So we are taking out the volume of the sand and we are putting it in a different field and we are spreading it out. So let us see what is the concept or what is the logic that you should apply in order to figure out the unknown that is asked in a question. So here the first point that we need to make clear is whenever you are digging out soil or whenever you are digging out sand from a particular place, what happens? Suppose it is a flat land, so without, it's a proper land without any deposits of soil, it's a normal land. You are taking out soil, what will happen? There will be a pit. You will be digging a pit by taking out that sand. Okay, so there is a land, so you are taking out sand from here. So what happens is there is a pit over here. Okay, now if you take out more sand, the depth of the pit will increase, right? Now depending upon the amount or the volume of the sand that is taken, the depth or the height of the pit will keep on increasing. Okay, now this sand is taken to another field and it is deposited in that field. When you deposit sand over a field, what happens? The thickness of the land will increase automatically because we are depositing sand over here. So there is a thickness which will increase. So our basic idea is the volume of the sand that is taken from this particular field will be equal to volume of the sand deposited in that particular place. Okay, you know the basic concept remains the same. Our problem is in applying with the formula. Now you know that volume of the sand taken from a place or from a pit is dependent on the depth or the height of the pit. Okay, now this is equal to volume of the sand spread out over a field. It will give a thickness or height T. You are clear with the concept? So if you are taking out the sand from here and assuming you are not having any wastage, you are putting it in another place, the volume has to remain the same. The sand that you take out from that particular place is dependent upon the depth of the pit, and the sand that you take and put it over there will increase the height of that particular place. Clear? Now let us apply this logic to a couple of sums and see how well you can understand it. Earth is taken out from a plot of size 7 meters by 10 meters and 2.5 meters deep. It is then spread uniformly over a field of size 10 meters by 5 meters. Find the extent to which the level of the field is raised. So basically, you know, as I told you before, there is a plot from which earth is taken. The volume of the earth that is taken out is equal to the volume of the earth that is spread on the field. So let us first find out the volume of the earth taken. It is equal to L into B into H. So it is 7 into 10 into 2.5. Okay. Now it is then spread uniformly over a field of size 10 meters. So volume of the earth on the field is again equal to L into B into H. So I will get 10 into 5 into T. Now since both of them are equal, I will get T is equal to 7 into 10 into 2.5 by 50. Okay, so I will get 7 into 25 by 50, or I will get 3.5 meters. Very simple sum. Just apply the basic logic and use the formula L into B into H. Now, there are multiple ways in which this particular sum can be asked, and this is the simplest way in which it can be asked. Now, let us go to a sum that is a bit more complicated than this. A plot has dimensions 240 meters by 180 meters. A drainlet 10 meter wide is dug all around it from the outside. Earth dugout is spread over the plot, increasing the height by 25 centimeters. Find the depth of the drainlet. Okay, so read the question properly. So you can see that there are most of the units are in meters, but then except the 25 centimeter one, everything is in meters. So I need to convert the 25 centimeters into meters when I am doing the sum. Okay, so what is given to you? A plot has a dimensions of 240 by 180. A drainlet of 10 meter wide is dug all around it from the outside. Okay, so I cannot directly apply the formula L into B into H because there is a drainlet which is going all around the plot. So let me see how it works. So my plot is of size 240 by 180. Now there is a drainlet which is dug outside. You know what is a drainlet? Let us say it is a canal like, the shape is like a canal like shape, it's a cuboid. So this is how it is, and they are telling that it is of the same width across, which is 10 meters. Okay. So here I have a 10 and here I have a 10. So here I have a 10 and here also I have a 10. Okay. Now the earth is dug out from this part. Okay. So when you dig out earth from a place, you create a depth over there. So there is a depth that is happening over here and that depth is uniform across. Now I need to find that particular depth. So let us call that particular depth as by x. It is uniform across. Now our main problem is we need to find the volume of the earth that is taken out. In the earlier sum, directly a plot and its size was given to you. So it was very easy, L into B into H. In this case, it is like a path which is moving around. So I cannot take the entire area because here is the place where the soil was put. I need to find out the volume of only this particular part. So let us see how we can find it. I am going to divide this part into small rectangular parts. You remember the sum wherein we were doing the polishing of the almirah, we divided the outside surface where we had the panels going into its rectangular parts. So here also I am going to divide it into rectangular parts. So here I have a rectangle. Okay, now I have got a similar rectangle over here. Okay, here I have two identical rectangles. So in short, I have basically two rectangles which are now 2 in number. Okay, 4 rectangles. Now, what is the volume of the earth that is taken out from this part? It is L into B into H. What is my length equal to? From here to here, it is 240. Here there is a 10, here there is a 10. So I get a 260. Okay. Here I have a breadth and I have a depth also, which we need to actually find, but the breadth is 10 into x. Okay, or I will get 2600x. Here also I will have 2600x. Let us calculate the volume of the earth taken from this small rectangle and this small part. What is the length of this part? The entire length is, no, I need to find only the length of this particular part, which is the same of this part. So it is 180. The breadth is a 10. So I can say that my volume will be 1800x. I hope you have understood how I got 1800. The length is 180 outside length. The breadth is a 10 and the depth is an x. Okay. The same volume I will have here also. Now, the volume of the earth taken out from across the drainlet will be from here, from here, from here and from here. I have to add up all of them and that particular volume is equal to volume of the earth that is spread over this particular area, which is again L into B into H, which is given by 180 into 240 into 0.25. Okay. Now, let us equate both of them and see what we are getting as a value of x. So I have equated both the volumes, and after equating, you can see that I am getting the volume of the earth taken out from the drainlet as 8800x, and that is equal to the volume of the field. So I will get the value of x by dividing the corresponding values, and so after solving this, I will get an approximate value of about 1.23 meters. Okay, so now this was a little more complicated than the previous sum, which was pretty much straightforward. But then I hope you have understood how to calculate the volume of the earth taken out from whichever part is given to you. Okay, we will do one more sum and we will move on to the last type of sum in this particular concept of volume of cubes and cuboids. A plot has dimensions 20 meters by 14 meter. A pit 6 meter long, 2.5 meter deep and 3 meter wide is dug in a corner of the plot. Earth taken out is spread over the remaining area. Find the extent to which the level of the field is raised. Now, you have a plot which is 20 meters by 14 meters. There is a pit 6 meter long, 2.5 meter deep and 3 meter wide dug in a corner. So, let us assume we have a pit over here. It is 6 meter long, 3 meter wide and there is a depth of 2.5 meters. Now, concept is the same. Volume of the earth taken out from this particular pit is equal to the volume of the earth that is spread across the field. Okay. Now, volume of the earth taken out from this pit is very easy to find because all the three measurements are given to us. L into B into H, 6 into 3 into 2.5. So much of meter cube. Okay. Now, the earth that is taken out is spread over the remaining part of the field. Now, when I say the remaining part of the field, the problem is that the field already has a pit there. Okay. So, now in order to find this remaining area, we need to subtract the area of this field from the area of the field minus the area of the pit. So, what is the area of the field? Area of the field is 14 into 20. What is the area of the pit? Length into breadth, which is 18. So, this is the area of the remaining field. Now, on this field, this particular earth is spread out, creating a thickness. So, volume of earth over the remaining field is this area into T or X, the thickness which we need to find. We equate that particular volume to this and then we find out the value of the thickness. Okay. So, you can see that I have calculated the thickness of the field by equating the volume of the earth over the remaining field to the volume of the earth taken out from the pit. So, when you are equating and solving for X, this is the value that you are getting. And because you are getting 0.1718 meters, you can also write it as 17.18 centimeters. Whichever you feel your teacher might appreciate, you feel is a better way of representing the thickness. Okay. So, now we are over with this particular kind of sum where, earth is taken out and spread over the field. Different kinds of pits and different shapes of field. So, I think you will be able to do any kind of sum that comes your way in this particular concept. Now, one more concept is there, which is a pretty easy one. I'll be doing only one sum in that particular concept. Then we will have just a review of all the types of sums which has come under the volume of the cuboid and we wind up the class. Okay. In the beginning of the class, I guess when I was taking the surface area of cubes and cuboids and I was introducing the terms associated with the cubes and cuboids, I told you the difference between a hollow solid and a proper solid. Okay. So, when I am talking about a cuboid, this textbook is in the shape of a cuboid. You can see that it's a solid cuboid. It is filled with pages. So, if this was made of wood, I could say that this is a proper cuboid made of solid wood. Okay. If I am asking you what's the volume of wood in this particular cuboid, you would say it is L into B into H. Okay. Now, suppose I am having a cuboid in this particular shape. This is a Amazon delivery box. So, anyways, so this is in the shape of a cuboid, proper cuboid. But then you can see that this part is hollow. It is not filled with anything. Okay. If I am asking you, suppose this is made of wood, I am asking you what is the amount of wood or what is the volume of wood that is there in this cuboid. I cannot do L into B into H. Look at this. There is no wood here. So what would be the thickness of the wood, or what would be the volume of the wood that I am using to make this particular cuboid? You know that outer part is made of wood, there is a thickness, and there is an inner part. So the outer dimension is different from the inner dimension, and the remaining part is hollow. So in order to find the amount of wood or the volume of wood used to make this particular kind of cuboid, which is a hollow cuboid, I need to subtract outer dimension minus the inner dimensions, or I can say outer volume minus the inner volume. When I am doing that, I will be eliminating this particular area, and I will be getting the exact amount of solid that is used to make this kind of a cuboid. So examples of this kind of a cuboid you can actually see when you are you're going into a shop and you're taking a pen stand made out of wood, which is in the shape of a cuboid. You can see that because you need place to put the pens and pencils, this part is hollow. The wood is there only here. Okay, so in order to find the amount of wood in that particular one, this is the method that you should be using. I hope why we are using or why we are subtracting the outer volume and the inner volume. So let us do a sum based on that. It's a pretty much straightforward concept. So let us get on with it. So guys, the external dimensions are 48, 36 and 12. Okay. Now when they say the thickness of the wood is 1.5 centimeters, you know that it's a thickness only on one side. Just to show, this is the thickness, right? So when they say the thickness of the wood, suppose I am taking the breadth, thickness of the wood here is 1.5. I need to account for the thickness of the wood on this side also. So in the case of length, breadth and the height, I have to multiply the thickness by 2 in order to account for the top part and the bottom part. So you can see that the thickness of the wood is 1.5 into 2, which is 3 centimeters, which I will reduce from each of the outer dimensions in order to get the inner dimension. Okay. Now I will find the outer volume by multiplying LB and H. I will find the inner volume by multiplying the inner dimensions. I will subtract both in order to get the amount of the wood in the box. So I have found out the answer for this part. Okay. Now I need to find how many erasers of size 3 centimeters into 1.5 centimeters into 0.75 centimeters can be fit into the box. When I am doing that, I need to know, I will basically use volume of the box divided by the volume of the eraser. One eraser, right? Volume of the eraser, I know how to find 3 into 1.5 into 0.75. I will multiply all three of them. How will you find a volume of the box? Volume of the box is given by the volume given by the inner dimension, because that is where I am going to keep the eraser. So I need to keep in mind that I need to take into account the inner volume. Clear? So I will find the inner volume now and divide by the volume of one eraser to get the number of erasers. So here I have found out the volume of the eraser 3.375. Now I know that the number of erasers is given by the inner volume divided by the eraser volume. So I have divided and I am getting 11,880 erasers can be fit into that particular box. Okay. So we are winding up the video, or we are winding up the class on the volume of cubes and cuboids. So before that, we will have a review of all the important types of sums that we have done in this particular class. So guys, here I have tried to concise all the points that we have come across in the different sums under the volume of the cubes and cuboids, and I have written it down over here. I think I have covered all the points. The first one is a earth taken out and spread in another field. You know the volume of the earth taken out, it will create a pit, and the volume of the earth that is taken out is dependent upon the depth of the pit. And that volume, when it is spread out, will increase the height of the field. So you have to equate both the volumes. The volume always remains the same, and then we find out the unknown component over here. Now the second one is a direct sum. You will be asked to find out the volume of a cube or a cuboid. Either the values will be directly given to you, or sometimes ratio will be given to you, and then some other relationship between the three quantities will be given to you, LB and H. You can figure out the individual values by using the ratio and that particular relationship. Now third one is a cube and cuboid in the water contained in another vessel. You know that the vessel is also in the shape of a cuboid, whose volume will be given by L into B into H, and the volume of the cuboid or the object that is dropped into the water is equal to the volume of the water that has risen in the vessel. If you are taking out the object, the water will fall. Even those volumes are equal. So you equate both the volumes and find out the height or the rise in the water level or the drop in the water level. Okay. Now the fourth one is a change of shape. You know that irrespective of the shape that the particular solid is in, the volume always remains the same. If a cuboid is converted into a cube, it does not matter, the volume will remain the same, and that is a basic concept here. Now a cube or a cuboid cut into components, again the volume remains the same. The only catch here is that I told you, you need to know whether a cuboid is cut along the length, the breadth or the thickness, so that you can take the component measurement into half. In the case of cubes, there is no such problem because all the sides are equal. So one of the sides will become a by 2 if you are dividing it into two parts or two components. If you are dividing the cube into 3, one side will become a by 3, a by 3, a by 3. The remaining breadth and thickness will remain as a. Okay. Now, sorry, this is the sixth one and this is the seventh one. The sixth one is hollow cuboid, which we just did. So the amount of the material used to make that particular cuboid will be external volume minus the internal volume. Okay. And in order to find out the capacity of that particular vessel, we have to consider the inner volume, not the outer volume. Okay. That also we have done a sum based on that. Now, last one is the water through a pipe that goes into a reservoir. One of the most important concept over here. The volume remains the same, is our basic idea, but the important point is the flowing water, which is the water through a pipe or a canal. Okay, both are flowing water. In order to find the volume, it is L into B into H. B and H we will definitely know, but the length is given by distance into time. Now, one of the most important things, please convert all the measurements into the same system, SI or CGS or whatever it is. So either it is all centimeters or it is all meters or all seconds or all minutes. Please do not mix up. Okay, and be very fast and very effective with the calculations in order to get the correct answers. The chapter is pretty simple. Please remember all these basic points, and then when you are doing the sums also, just recheck, cross-check, verify the point and all this concept and how you effectively are applying it into the sums. And you know where to contact me if you have got any doubts regarding the contents of this particular class. Okay, so keep practicing. Now next I will be taking the surface area of a cylinder, easy one. So bye.